Good evening, everyone. Hopefully everybody can hear me and the video is working and nothing's exploded on my computer yet. Keyword. My name is Rick Henderson. I'm the president of the ASKC. Would like to start this evening's meeting, the March 2021 general meeting. So I'd like to say hello to the ASKC members that are joining us via Zoom and also the general public that are watching us on Facebook. So I'm going to skip ahead just a little bit. We have a special guest tonight, David Levy. He's going to give us a special greeting to everybody. So David, if you're there.
Yes, I am here.
Okay.
And I am.
See if the video and everything. There you are.
Video. And I hope you can all hear me. I'd like to add my welcome to all of you tonight in this wonderful meeting that we are about to have. We're going to have a very exciting lecture, and I hope to be able to join you a little bit later on. Although I have to run off to another meeting. I'm using the transporter tonight, it seems. Anyway, for my quote of the month, I thought I would share a little wisdom from William Blake. In the year 1803, he wrote Auguries of Innocence. And it starts like this. To see the world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Well, in 1 hour and in the palm of our hand, we hold a beautiful thing tonight, the monthly meeting of the Astronomical Society of Kansas City, one of my favorite groups. Let's enjoy it. And it's going to be a great evening. We'll hold all that in the palm of our hand and eternity in an hour. And back to you now. Thank you.
All right. Thank you, David. Always a pleasure to have you join us. So Jackie, I'll ask Sarah to start her video and I'll let you go ahead and introduce our guest speaker for this evening.
Okay. Well, I heard about Sarah from a friend of mine in astronomy, and she went to school at Kansas State University where she got a degree in geology, I believe. But I think she has a couple other degrees too, like in chemistry and geography. And I went out on the internet yesterday, snooping around, looking for information on her. And I found out that she had a little bit of trouble getting believed that she was a woman of science, getting into the field and stuff. You know, Sarah, I want you to know that I had the same problem in 1965 when I went to school at the University of Kansas, and I was a math major, but I was taking science, and I was in this class. They had 4 sections of calculus and I was so nervous that year. I studied so hard that fall, and when midterms came, I studied really hard. And anyway, when they found out the next week, and when I came to class, they said, well, you know, the curve is really messed up on this one because somebody got more than perfect on their score, and we had to throw that out in order to make the rest of you look good. And he said, that person is in this class. And the guys were all looking around, you know, and it was me. So you stick with it, girl, because many women like I tried to pave the way for you. And I'm just thrilled that you're doing what you're doing. And you're studying what, Mars rocks, because you have a geology degree on the Curiosity Rover, and you were a team member on that for like 3 years, something like that.
Yeah.
Huh?
Yes.
Yes. And now have you finished your PhD in planetary science yet? Or are you still working on that?
So I'm just a master's student at K-State.
Oh, okay. But they said something about you were working on a PhD though.
Oh, yes.
That's all.
So that was true. After my bachelor's at K-State, I went to a new PhD program in planetary science, but it really wasn't up to my standards. So I left after a year and a half and came back to K-State kind of to figure out what program I was going to try after this But K-State, my master's, is kind of just like a step or a stopgap, just to figure out where to go next.
But you do return to Kansas to promote science to your students. So that's a wonderful thing to do. Now, this is what I found on the internet. This is currently what she's doing. Creating a Raman calibration for chlorite minerals that will have applications for both Perseverance and ExoMars missions. Well, I don't know what a Raman calibration is, but maybe I will find out.
Yes,
So,
I have a little bit about that in here.
Yeah.
So,
well, welcome to the Astronomical Society of Kansas City, and we're so glad that you're with us. And take it away.
all right. Okay, so I'm here to talk about the Mars rovers, Curiosity and Perseverance, and also how I've supported the missions. So this is about 2 weeks out of date, but so it's about going to be like Sol 3070 on the Curiosity mission, and then it's going to be about Sol, I would say about 4035 on the Perseverance mission. So a Sol is a term for Mars Day. And we give it a different term because a sol is actually 24 hours and 37 minutes long. And both rovers' prime mission is 1 Mars years or 687 sols. So the Curiosity has already blown past that. They have successfully completed their prime mission. And Perseverance, if you know, just landed on Mars in February. So it has quite a long time to go before it can be considered like a successful mission. So just a brief history of the rovers. The very first rover was Sojourner in 1997. That one had a prime mission of about 1 week, and it lasted 90 days. Then Opportunity and Spirit, they had a prime mission of 90 sols, and Opportunity lasted 14 years, and Spirit operated for 6 years. So much longer than their prime mission. And then Curiosity already met its prime mission about in 2014, and it's still going on today. And then Perseverance just landed. So Opportunity and Spirit were twin rovers. Curiosity and Perseverance are not considered twin. They have a different design. On the outside, the general look is similar, but all of the instruments have changed. So they are technically not twins. So Curiosity, this is the mission that I was a part of. Its primary scientific goal is to explore Gale Crater on Mars as a potential habitat for life past or present. Curiosity does not have the instrumental suite to actually discover life. It just doesn't, unless it's blatantly obvious, which it's not going to be. But it does have an instrument suite to look for different parts of like geology, geochemistry. It can look for past signs of water, different building blocks of life like carbon, hydrogen, nitrogen, phosphorus. It can look for those things. So Curiosity's goal was to never look for life directly. It was to look for things that show that in the past or currently, Mars could have had life. Because if Mars never even had the environment for life, then it was never going to just magically have life. Gale Crater was chosen because the orbiters around Mars showed geological signs that water used to be present, like dried out riverbeds, different clay minerals, things of that nature that showed water used to be here. So for Curiosity, it has 11 instruments. I'm going to start in the top left with MassCam. So MassCam is imagery. It can take images in different spectra, so it can be used scientifically, but in the public setting, it's known for the very high resolution pictures of Mars. They're the ones that get displayed quite often. Then we have RIMS, which is weather. It can detect like temperature and wind. Then there's DAN, which is subsurface hydrogen. It can shoot neutrons at the ground and detect hydrogen up to about 1 meter underground. Then you have SAM, which is chemistry and isotopes. Then you have ChemMin, which can determine mineralogy. Then you have MARTI, which is the descent imager. Then we move on to the arm, and remember that we consider Curiosity and Perseverance to be essentially robotic geologists. So a geologist is going to have a drill. We're going to have a scoop, brush, sieves. And then on the arm, we also have APXS, which uses X-rays to determine chemical composition. We have MAHLI, and that's how we say the M-A-H-L-I, MAHLI. That's imaging. So it can take very close pictures of rocks. It's actually the Mars Hand lens. Then we move over to RAD, which is inside Curiosity. That detects radiation. That's actually, those data is actually going to be used more for like human space flight in the future. And then ChemCam. So ChemCam is in yellow because I'm biased, because that's the instrument I got to work on for 3 years. So this is just a fun picture I like. We had a speaker at K-State, and she brought an actual display of the Curiosity rover wheel. So it's from about my hip to my knee. And what you should notice is that there are 3 lines that have holes in them, but those lines are not identical. That is because that is Morse code, just reversed. So the top line is J, the next line is P, and the last one is L, which stands for the Jet Propulsion Lab. So NASA Jet Propulsion Lab took all the instruments once they were built, and they were the ones to do the final assembly of everything. So now Curiosity just roves around on Mars, imprinting JPL on everything. So since the wheels were not considered a specific instrument, it was up to JPL to design them. And one of the things they needed was holes in the wheels to let out sand, let out rocks, because those wheels are mostly hollow. So you don't want a lot of sand collecting in there or rocks. You need a way to deposit that. And they thought they were being clever by putting JPL in Morse code. So my first internship on the ChemCam team was in 2016. I was at Los Alamos National Laboratory, which is a very strict laboratory. I was not allowed to ever take pictures of myself unless I had prior approval. So these 2 photos are the only pictures I have to prove that I was ever like at Los Alamos National Lab. I don't even have pictures from like my subsequent interns or internships there. On the picture on the left, I am standing in front of what we call a Mars chamber. So we pull out the pressure and the oxygen, and then we pump in carbon dioxide. That way, when we shoot any samples, and we shoot samples with lasers, and these lasers can go through the window. So anything we shoot in there should be under Mars pressure. So a lot less pressure and a lot more carbon dioxide. And what we're doing is we're trying to see if the same results we get through the Mars chamber is what we're seeing on Mars itself. And then on the right, it's hard to tell, but in the bottom right, where you can kind of see a fan, that is the ChemCam engineering model. That's what we have on Earth. So ChemCam, this is the instrument, uses lasers to take chemical composition of rocks. So it can tell you that there's 70% of silica in there, 20 of iron, or whatever. So the laser's on the top of the rover, and it can turn and shoot places for us. So that's what a ChemCam spectra looks like at the bottom, all those little jagged lines. And then on the right is just one example of a target we've hit. The white dots on that meteorite are actually where we shot it with the laser. So we pretty much took off the coating of a meteorite. Those locations are pretty small. They're smaller than a millimeter. And we normally take about 5 to 20 sampling locations per target. And then the reason we call it cam is just because it's a camera, and we've taken pictures to see like where exactly are we shooting. Because sometimes we'll get chemical differences in a rock, but the rock on the surface looks the exact same. So it's kind of a fun mystery of like, when are things going to be significantly different, but they look the same? So here's the ChemCam engineering model I was talking about earlier. That's the exact one we use on Earth. And then on the right, that is a rock being shot with ChemCam. That little blue dot on the rock that's on the stand, that is it. Our laser is actually invisible, so we cannot see it, but we can see its results. So when our laser is focused, hitting a rock, it explodes with plasma because it's that powerful. That plasma can then be read by our spectrometers to see how that light is actually broken down. And that is what we use to determine chemical composition. These are just targets we've had in the past. So this one, again, is the meteorite, and now it's just blown up. And you can see those little dots of where our laser just like chipped away at the coating. And then the picture on the right is showing what it looks like just in bedrock, where we're just going dot, 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 dot. This was something interesting that they didn't know or really think about until it was already on Mars. So ChemCam is a class 4 laser. For those who are familiar with lasers, class 4 is the highest. So that's also the most dangerous. You have to take a lot of special precautions to be around them usually. So you don't take a class 4 laser and just like take it outside. You have it in a nice laboratory. Well, when you bring rock samples into the laboratory, they're normally like mostly cleaned off or mostly had the dust knocked off of them to begin with. But ChemCam on Mars, it's not in a laboratory, it's just outside. So when our laser hits something, there's so much blowback that dust just gets knocked away. And that's not something they really thought of or expected, I don't think, which is really interesting because also why would they have ever thought of that? Because they didn't get to test this outdoors. They were always testing this in a laboratory. Then next, so the picture on the left, if you can see that tiny burn dot in front of Lincoln's nose, that is how small our laser is. That is all we need to vaporize things. And we can tell so much data from those little points. So the picture on the right, that's a drill hole on Mars. That's the size of a dime. And because ChemCam is so high, it can just like go down inside the whole forest. So we can get like a gradient of how the things are changing between layers. So this is a real Mars photo from Curiosity, but the team uses NavCam, which is navigational cameras, to pick targets when they're doing operations. This is actually a mass cam photo, but this is just a simplified example of picking targets. So while I was on the team, I got to be trained on operations. I normally did downlink. So uplink is when they look at where they are, decide what targets they hit, and then downlink is when I get all the data down and I make preliminary reports to say, the laser looks good, nothing weird, everything is roughly as expected, or if things aren't as expected, like did we hit high silica, did we hit high manganese, then I will go tell them. And hopefully I tell them before they do operations for uplink. That way, if they need to change anything based on my preliminary reports, they can. So NASA will normally tell you, ChemCam, you have 3 targets. That's what you're allowed to go pick. And then anyone can technically like voice their opinion, but only the uplink person of the day gets final decision. And then we have someone on engineering who double checks to make sure that that is safe, because we do not shoot into the sun. We don't shoot where the arm is. And there's a few other rules. So basically, uplink is just making sure that these targets are a good idea, like scientifically they're good. And then also, like, is this safe for the rover? Because I think one time they came very close to shooting the arm. So we should never shoot the arm. So what did Curiosity find? Well, Curiosity found evidence that there was persistent liquid water in the past. It's not just like there was water and it just evaporated really quickly. Like, it was there for a long time. Curiosity also found that there was sulfur, nitrogen, oxygen, phosphorus, and carbon. They found organic carbon in rocks. They found a present and active methane cycle in Mars's atmosphere. Now that could be just due to the breakdown of minerals with water, specifically subsurface water. They found that radiation could pose health risks for humans, so that is helping them decide, like, if we do human space flights in the future, how are we going to do that? And then they also found a thicker atmosphere and more water in Mars's past. So what did I do to support the mission? I got to look and track manganese minerals. So concentrating manganese takes liquid water in strongly oxidizing condition. Now, we already knew that Gale Crater had liquid water. We found that it had liquid water for a long time. So that part we checked off. But we didn't think that Mars ever had the strongly oxidizing condition. So manganese is a redox sensitive element. It's very similar to Mars. So when Mars easily rusts, that is a redox reaction happening. But manganese needs more oxidation potential than iron. So concentrated manganese on Earth, manganese deposits were only observed after the Great Oxidation Event on Earth. And then after that happened, microbes took over the processing of making manganese oxides. So now almost 99% of these minerals on Earth are formed by microbes. So if we have high manganese concentration on Mars, which we found at least 20% of manganese in some rocks on Mars. And the average is like 0.1%. So that's a huge, huge difference. So it has implications for just redox, so reduction in oxidation, and habitability. If these formed, even if they formed just because there's oxygen in the atmosphere, that changes what we know about the atmosphere of Mars. And then I also did some geomicrobiology work. So what I was trying to do is I took 2 different microbes and I gave them manganese that was not solid. It was just floating in the solution. And I gave them 2 weeks to see what kind of minerals they produced. And then we took off the minerals and then we used a scanning electron microscope on them and we shot them with the laser to see like what are the difference between these 2 types of microbes that were given the exact same elements. And then back to what I was doing for Lannel on Mars, I also have some mapping skills. So this is Gale Crater. This is a very small portion of Gale Crater. I think this was towards the end of my 3rd internship, or maybe 2nd and 3rd. But we are headed downwards towards Vera Rubin Ridge. And Vera Rubin Ridge from orbit, we could see had oxidized iron in it. And that gives a good idea that there could be an increase in manganese. That was the thought. So Vera Rubin Ridge is at the very bottom. It's this red little bit that's just peeking out. So this area before, it's called the Murray Formation. It formed during when the lake was there. So as we are moving up the mountain towards this oxidized ridge, we start hitting loads of high manganese back to back to back. So pretty much anything that is red, orange, or yellow, we are considering to be high manganese for Mars. Blue is anywhere between low and average, and then green would be slightly above average. So you can see that there are just different parts where there's just clusters of high manganese. So we think this means that the lake experienced a change in redox conditions and was more oxidizing during the formation of these rocks right here. I then went and got all the pictures for the rocks. We found that 63% of high manganese is in a dark toned area, which is pretty reasonable. Manganese is what we call a transitional element, which means it's typically darker and adds a lot more color. We found that 77% of high manganese was found in what we call nodules, and then 34% was in nodules, and then 43% was in these erosion resistant plates where you can see like they formed a layer, but then one layer was weaker and just got eroded away. And then some were just like massive rocks, layered bedrock. So that was 2 different projects. Those were both during my undergrad. And then right now at the Kansas State University, I'm in the Raman lab. So this is where I've started shifting more to supporting the Perseverance mission. So in this picture, you can see our Raman spectrometer. This is a different type of laser. So this one's a class 1. So the laser operates inside that chamber, so I never get to see the laser. So I'm looking at what we call chlorite. It's a mineral. Specifically, it's a layered clay mineral, and you can kind of see its layers right here. On the right is a thin section, and the chlorite is the green piece in the top right-hand corner. So what makes this mineral important is that it's a clay. Normally it forms with water, so we can find it on Mars. We've actually detected it with orbiters, so we know it's on Mars. It's theoretically in Jezero crater, which is where they just landed Perseverance. And chlorite likes to change its chemical composition based on temperature. So for example, it could have iron if it's at lower temperature, but if it gets hotter and hotter and hotter, it will switch out iron for magnesium. So I'm using chlorite and Raman to see if I can determine what the chemical composition is with this laser. So these thin sections that the slide is on, that's actually a very common thing we do in geology is we take our rock and we slice it as thin as possible and mount it on a slide just because it's easier to use. And sometimes if it's thin enough, you can actually get light to come through it and you can tell different properties. So I've been using different chlorite thin sections and we've already got chemical composition from them from an electron microprobe. And basically I'm just seeing, can my Raman determine when there's enough, like when there's X amount of iron, and can it determine when there's X amount of magnesium? So the goal would be that once I have my whole calibration complete, that NASA or the European Space Agency with their rover can use their respective Ramans, hit chlorite, use my model, say there's X amount of iron, and then go on one step further, use someone else's model that says, if you have this much iron in chloride, this is the temperature formation. This is the conditions Mars was under. So I'm sort of like a puzzle piece. Like we already have models that say this chemical composition means this temperature formation. And NASA and the European Space Agency already have these Ramans built and put on their rovers. But they don't have the right instruments at the moment to use those other kind of models to determine temperature. I would be that building and that bridge between the two, so they can use their Ramans to determine temperature formation in a very long step path. So this is what it looks like under the microscope. It's these kind of green looking thing and it like fans out. It can actually look multiple different ways, which makes this a very difficult mineral to deal with. So Perseverance, it's the newest rover. So it's actually named by a student. I don't know if you guys know this, but all Mars rovers are named named by students. The Curiosity rover was actually named by a 7th grader in Olathe. So that's pretty cool. For Perseverance, the very special essay he wrote says, "We, not as a nation, but as humans, will not give up. The human race will always persevere into the future." And I think that's a really good name. I think especially after the last year we've had, Perseverance is a pretty fitting name for this newest rover. So they engraved the name and then they put it here on the arm. So it actually helps protect some of the wires inside. And Perseverance's primary scientific goal is to explore Jezero crater on Mars for biosignatures. So Perseverance actually is out there now looking for life. That is what it's trying to do. And it's also going to try to create and drill core samples that we can bring back, and they are preparing for humans to land on Mars. So some of the differences between the Curiosity rover and Mars 2020. So there's another stabilizing bar, the caching system, which is going to collect these rocks, the turret, which can hold even heavier science tools than before. It has 23 cameras, mostly in color. Curiosity only had 17 cameras, and I'm not sure, but I know a decent amount were black and white. And then new wheels, because Curiosity's wheels got beat up more than they thought it would. So this is Curiosity's wheels. They tried to do the design after where I believe Opportunity landed. Opportunity landed in a place where the sand and rocks were pretty giving, so they would just kind of like fall over. Curiosity did not land there. So when it tried to like roll over a rock, it just like sunk down on it and just kept puncturing wheel after wheel. So that is Curiosity's wheel, and that is Perseverance's. So this is Jezero Crater. This is one from orbit, and they've overlaid it with special colors and spectra, and that can tell them like what minerals are present. So they have thought that chlorite, the mineral I work on, is in this crater. So that's something I'm very excited for. The yellow star down here is where Perseverance landed. To the left here, you can see that there was a river channel, and that it came out here and made this delta and filled up the rest of the crater with a lake. So there's a lot of interesting geology processes that are happening right here. And they thought this was going to be the best place to look for life, but more specifically preserve life. Because if there ever was life on Mars many, many eons ago, and if it didn't get preserved, then there's no point of going to that place, even if life was there. It has to be preserved in a way we can determine it. So that's why they went to a delta with clay minerals. Clays are very good typically at preserving life. And this is at the moment the model that this is the track they want to go to get up into the riverbed. So we landed at the bottom and we're trying to go work our way up. So this is Perseverance. You can already see this is significantly less than Curiosity. Again, it kind of looks the same, but you can now start to tell there's different parts of it that makes it different. So they have Mastcam Z. So that is like Mastcam, but it can now do zoom. There's RimFax, which can do subsurface radar. So it's trying to look for water underground in a slightly different way that they and Dan did. There's MOXIE, which produces oxygen from the carbon dioxide in the air. So that oxygen can be liquefied for rocket fuel. It can be used for what humans are going to breathe. So MOXIE itself doesn't support the Perseverance mission, in my opinion, but it will support human spaceflight. Then we have Pixel out here, which is an X-ray spectrometer. Then we have Sherlock, which is an ultraviolet spectrometer. So it has a Raman laser. It will have specifically a UV Raman, which is really good for determining organics. You have Meta, which is a weather station. It can also determine radiation. And then last is SuperCam, which will have the laser that I worked on before and Raman. So I actually have experience with both lasers that's on SuperCam. And NASA loves its Easter eggs. So the picture on the left, that is the Mastcam calibration target. So they take pictures of this and then they know already like what the colors are actually supposed to be. So if they take pictures anywhere else on Mars and they think the colors are off, they can just use the calibration target to like correct the color. And you can see these fun things around it. Like it says 2 worlds, 1 beginning, talking about how Earth and Mars formed at the same time, even though we're 2 different worlds. So they have a picture of our solar system, or at least the inner part. They have the DNA structure. They have some kind of bacteria, I believe. They have plants, dinosaurs, humans, rockets, kind of showing the evolution of Earth. And then on the right is a plaque they put on Perseverance. And it's specifically supposed to be for the healthcare workers that died during COVID. So this is the Sherlock calibration target. So Sherlock's camera is actually named Watson. This one in the middle, I believe, is a meteorite, a Mars meteorite that they've brought back with them. And they call the calibration target 221B Baker Street. And for anyone who has read the books or seen any Sherlock adaptation, that is where Sherlock Holmes lives. So I thought that was a kind of clever thing that they just keep adding more and more jokes to it. Then they have this little plaque. In the real picture, you can see these 3 little squares. Those are silica microchips, and NASA, for most of their missions nowadays, they will allow you to send your name in, and then they'll like sketch like as teeny tiny as they can your name on these microchips and then put them on the actual rover. So that's what it's saying when it says about 11 million explorers. It's that 11 million people around the world put their name and sent their name into NASA and got their name on these microchips that were then sent to Mars. Some of you might have heard about the Perseverance parachute. So it's written in binary. So if you look closely and if you like go back and forth between the two, you can see that it says "Dare Mighty Things," which is the unofficial slogan at JPL. Oh, and then like around that outer ring, that is coordinates to JPL. Okay, so they finally landed successfully on Mars, and this was the first picture they got back, or the first colored picture. And it's not that shocking that it's underneath the wheel, because both Curiosity and Perseverance actually recorded their own landing. So I would suggest that you guys check those out. The video was a bit too long for this talk, but they're really interesting, especially if you go from Curiosity to Perseverance. Perseverance is just so much better high resolution that it's just so unbelievable. So these are some of the first pictures they started to send back. They don't do scientific operations right off the back. They want to make sure that everything's in working order. So they're making sure that it's moving correctly. The wheels are, the arm is. Can they do some test drives first? Because they want to know like where all the problems are before they start going. This is a picture that they took of their surroundings. So this is just so interesting to me, at least as a geologist, because you see kind of like the sandy area, you get into some rocks, and then you get into a whole nother geological formation. And I believe this picture, that mound is about a mile away, so not too far. And I think their goal is to like go around it. On the top right, that really long flat rock, that is SuperCam's very first target. And then this is a video of its first drive. And you can kind of see, it's kind of hard to tell because Perseverance is like taking the video as it's moving forward, but then it like turns its head back around to look at its wheels. So we can do that one more time. So going forward, and then we start to turn. Oops, sorry, I didn't mean to replay that. And that's the picture looking back at everything. And then last but not least, Ingenuity helicopter. This is what they're about to get ready for. They drove to a spot. They, I believe, just dropped it off, or maybe they are about a day or two before like dropping it off. So that is riding under Perseverance's belly. So what they're going to do is let it drop. Perseverance is going to just keep driving, and then they're going to do a test flight to see if Ingenuity can actually fly. The only thing Ingenuity has on it right now is cameras. It doesn't have any scientific instruments. They're hoping to do both a test flight, and if that works, there are talks that they want to start using it essentially like as a scout or a drone, where it flies around the area and then comes back, and they can use its pictures to determine where Perseverance should drive next. Oh, and then sorry, I forgot, there's last thing, the Mars sample return container. So what we want to do is drill a bunch of cores on Mars, put them in this container to eventually get picked up. So this is what a sampling tube looks like. There's titanium nitride coating, there's some lock, a serial number. The sample return mission, which I think they don't even plan for us to have samples until like the early 30s, mid 30s. It's 3 parts. So part 1 is Perseverance. Perseverance has to land successfully on Mars, then successfully take rock samples for us. That's part 1. Part 2 is a completely new mission. It's called the Sample Retriever Lander mission. So it will be ran by NASA, and that's the top, or those are the side pictures. So there's 2 ways to do it. They're still in talks about exactly how, but one of the thoughts is they have a lander on Mars. It deposits a teeny tiny rover, kind of the size of Sojourner. The little rover goes out, grabs the samples, returns it to the lander. The lander then shoots that little probe into the air. And this is then mission 3. It's the Earth Return Orbiter. So this is actually a partnership with the ESA, and they are in charge of that last step. So the ESA will send an orbiter to Mars, and it will just like orbit around Mars, and then the lander shoots the probe, the orbiter catches the probe, and then has to like get itself out of the Mars's atmosphere in orbit, and then it comes back down where someone collects it. So they think this is going to take, again, maybe to the early 30s, if not slightly longer, because every step has to be perfect. And this is one more Easter egg, the very last one that I'll mention. So this is another thing that they put on Perseverance. And it's both nice because it's kind of showing like the family history, Sojourner, Spirit, Opportunity, Curiosity, Perseverance, and Ingenuity. And it shows how progression it is. And it really reminds me of the quote, like, we can only see further now because we stand on the shoulder of giants. Because Perseverance could not exist without all the work that Curiosity, like all the work that engineers and scientists put into Curiosity, which is the same because Curiosity could not have existed without everyone who worked on Spirit and Opportunity and so forth. So it's kind of interesting as a planetary scientist because sometimes like my work like won't be recognized or won't be used for a few years down the road. But then when it does, it gets reused and built upon in grand ways. It's not something that we always necessarily see like the direct benefits instantly. Sometimes it comes much later. And with that, that is my last slide.
Great, thank you, Sarah. Let's see. So, are you open to take some questions if anybody in the audience presents them?
Yeah.
Okay. So we're looking at both the chat windows and also the Facebook comment page. I can complete a sentence, honest. I can do that. Let's see. So far, I'm not seeing anything. I think you must have just wowed everybody so much that they're speechless, which is a pretty good trick with this crowd.
Yeah, well, it's really hard trying to fit in all those topics into a 40-minute presentation.
True. I did get one comment that said, I don't have a question, but I just wanted to say that was a great presentation. So I do have a question. Like you went to Los Alamos, were you ever at JPL itself as well?
Okay, so that's a funny story. No, I was not at JPL at the time. I was only at Los Alamos, but I just started working remotely for JPL a month ago, but not on Perseverance, on a completely different group and project. So I'm doing data analysis for LIBS and Raman. Those are the 2 lasers that I work with typically. So.
Okay, that's cool. Yeah, California's way overrated anyway. So, okay, we've got some questions coming in. Michael O'Keefe said, said, you said that Jezero had potential to hold onto life. Was that life or evidence of past life?
I think the feeling amongst planetary scientists that Jezero, if Mars ever held life, Jezero would be a candidate for preserving it. I don't think anyone really thinks that Mars has life on the, at least on the surface, that could be preserved. Mars has a very weak atmosphere, and the UV rays from the sun would just like pretty much kill any of the microbes, or at least kill and distort their DNA so much they couldn't even reproduce. So we're thinking more on preservation than actual like finding living life.
Okay. So we got another question come in. This is from David Levy. He says, he asks you, what inspired you to go into planetary science and to do these incredible things? That's a good one.
Yeah. I don't know. I always kind of liked science. I was always someone who was just like messing around with things at home. I would do the like the canister rockets where you would put lemon juice and baking soda and have it shoot off. So I think I just liked planetary science because I could implement a whole bunch of sciences at once, and I was never tied to one. I forget if Jackie mentioned it, but I have 3 bachelor's degrees in chemistry, geology, and geography. And if I'm being honest, not one of them is really my favorite. And I really liked having all 3 of them. I like using them all at the same time. So that's what I kind of like about just planetary science, is that I'm allowed to use all 3 of them at once. And anything in planetary science is normally new and groundbreaking because there's just so much out there that we haven't been able to do yet.
Okay. Just as a side note, earlier when I introduced you to David Levy, when he was working with the Comet Shoemaker-Levy 9, Gene Shoemaker was also a geologist.
Yeah.
Okay. Let's see, more questions. I guess people are figuring out how to type now. Bill Barlow is asking, is Perseverance in an area that might see some dust devils?
I actually don't know that. I think so. I think dust devils are pretty prevalent everywhere on Mars, but I'm not 100% sure on that.
Okay. Terry Connor. Terry was actually a high school science teacher and engineer as well. She says, great job. Could you comment further on your comments about the clay-like deposits being the best for preserving life, and what are you looking for?
So I guess there's a few things. One, clay typically forms with water. So if you want to find microbes or life, you tend to follow the water. So that's part of it. And preserving life. So the way clays form, typically they're in layers. So it's easier for them to just kind of like stack upon the microbes. And unless I'm confusing some of this, but some of those clays can be used by the microbes to like continue their own life cycle. So like clays or microbes might be just in general found more around clays than they would say different minerals like olivine.
Okay. Let's see. There was a comment from Alan Lehman that said NASA has published some photos of dust devils by Perseverance. So I guess they do have dust devils.
Yeah.
More questions. And I apologize if I mispronounce the name. I think it's Gautam Ankam. He says, great presentation. And what is the major difference between the instruments that detect life and instruments that detect the factors that determine factors needed for life?
Okay, so for example, on Curiosity, we had ChemCam, which is a LIBS laser, which is laser-induced breakdown spectroscopy. So all it could do was tell you the percentage of silica, etc. Also, APX did the same thing. It would just tell you the percentage of silica. Like, that's not very useful information for actually trying to define life, just because if you find something with the same percentages of elements as life, then you can't actually determine the two. Curiosity did have something called an XRD, which can determine mineralogy, but even that, it's not good enough because you can't always tell if the mineral was produced by microbes or if it's just natural. Now, Perseverance, it will have Pixel. Pixel can look for biofilms, which is created by microbes, and I don't think they have found a way yet where you can create that just like in a laboratory. So that's something that they're looking for. Then they're looking for different types of organics. Like they're hoping to find as many organics as possible, specifically ones that can never form or they've yet to form just by like chemical mechanisms. So that's kind of what they can detect nowadays on Perseverance. And they can also still so Raman spectroscopy, which is what I work on at K-State, they have that on Perseverance and 2 different lasers, and those can also determine mineralogy. So if you can look at something and be like, I think this was formed by microbes, and then determine like the organics around it and use pixel to look for more teeny tiny biosignatures, they'll have a lot better chance.
Okay. All right, let's see. Boy, more questions. Gerald Williams has 2 questions. He's ganging up on you here now. His first one says, what wavelength or frequency does the Raman laser use?
So the SuperCam one and the one at K-State is a 520 nanometer. And then Sherlock, which is the UV Raman, I always mess it up, but I think it's around like 380, 360, somewhere between there. So that's the UV one, and it can look for organics.
Okay. His second question, he says, concerning clays, do you mean preserved life or fossilized life?
Probably more fossilized, but I think we're getting to the edge of my knowledge of how much I know about microbiology.
Okay.
Sorry.
All right. Well, you're still way ahead of me, so I'm okay. David Young, let's see. I'm not sure if that's a question for you or me. Anyway, Alan Lehman's asking, can the ChemCam get spectra from dust in the atmosphere?
I believe it can. I'm almost certain that it can. But since I was primarily looking at rocks, I would just toss anything that said dust off, like out of my database. So I don't know where we were getting all the dust spectra from, but we had some, and I would just get rid of it.
Okay. I think I just finally figured out what David was asking. David Young asks, where are the samples, and I'm assuming the samples that would be retrieved by later mission. He says, where are the samples stored?
I believe they will be stored on Perseverance, though I know, and I don't, since I'm not on Perseverance, I've not kept up with all the details. They've been talking about a lot of different ways. One of them, they talked about doing the samples like an Easter egg where Perseverance would just drop it behind them and then something would come collect them all, because they thought that way, if something goes wrong, you can at least get 6 samples and you're not losing all 30 of them. And then the other way, I think, is to really do like take all 30, keep them together, and something collects all 30 at once. I don't know if they finally decided which direction they were headed. I don't know if they can still do like go back and forth, or if they've like pretty much solidified on one direction.
Okay. Let's see, another question here. Bill Koch asks, he says, great detailed talk. And what new and exciting things do you see yourself doing in the future?
What do I see myself doing? Well, I'm hoping to graduate with my master's in this August and go on for a PhD. We're still waiting to hear back on all of that, just because budget cuts have been everywhere across the board. So do a PhD, probably in geology or planetary science. And then after that, I would like to work for NASA or maybe Los Alamos National Lab again. And if the opportunity presents itself, I would like to be an astronaut, but I know how like competitive and cutthroat that kind of is. So if it happens, that's great. And I'll definitely keep trying for it. But if it doesn't, I understand. I'm hoping to do things in grad school to boost my application. Like there is a group that goes to Antarctica to look for meteorites. So I'm hoping to get on that team for like a season. And I'm also looking to do like international experiences.
Okay, great. Interesting. Dave Brackey just posted a comment, said the Apollo program had pictures of young engineers in the program. He says your photos seem to show young people. So are you planning on making a career of space exploration?
Yeah.
So
Go ahead.
who would? Oh, yeah, I think I missed the boat. I would have loved to have done that. Okay, Chris Adrian is asking, not sure if you know, but are there ideas of how the Martian subsurface would support foundations if we were to build structures? If not, are there plans to start gathering that info with Perseverance?
I assume that's part of what the radar is for is to look for both water, but also like the structure. And anything further than that, I don't know. I'm sorry.
Okay. Let's see. Another question. Bill Barlow's asking, has the rover taken any pictures of the Martian night sky? He's assuming it must be very dark with a thin atmosphere.
Perseverance has, but I know Curiosity has. And it's actually a blue sunset because of the way the light diffracts through the atmosphere. So we definitely have blue sunset photos from Curiosity.
Okay, cool. Let's see. Okay, the questions seem to have died down. Let's see, is that another one?
One for Gerald, a couple of Geralds.
Yeah, I read his. Bill Koch saying he's as if you go to Mars, just don't pull a Mark Watney.
I don't know who that is.
Oh, the movie The Martian?
Oh, yes. Okay. Sorry, I was thinking like an actual scientist, but yes, you're right.
Well, he probably should have said, don't pull a Matt Damon. I don't know.
That I would have gotten. Yes, right away.
Okay. Yeah, Jackie, I saw the two questions from Gerald, and in fact, I'd already read them about the wavelength and the clays preserving or fossilizing.
I must have been daydreaming.
Or night dreaming. Okay, we had another comment. Just a comment. James Marshall says, thank you very much for a great presentation. Okay, I think the questions have kind of died off now. So, Sarah, thank you very much for taking the time to make the presentation. I'm only a little bit jealous. So, thank you very much. And I hope we see you again. So keep us posted. Sounds like you're doing some really fun stuff.
Yeah.
If you're ever in Kansas City, you can come by and we'll take you out to Powell Observatory. We have a 30-inch Newtonian telescope out there.
Ooh, okay.
Oh yeah, definitely. You have a standing offer, or in this case, a sitting offer. So.
All right. Well, thank you.
All right. So
thank you, Sarah.
Well, thanks a lot. I'm going to sign off. So Sarah, you have a good night, and everybody else, ASKC land, and Facebook. Thank you for attending, and everybody stay safe, and we'll see you next time. Good night, Sarah.
Bye.
Okay, once again, I'd like to welcome everybody to the ASKC general meeting. So let's see, first thing is David Young, our observatory director. David, are you there? Can you join us and give us an update on Powell Observatory?
Yeah,
Yep,
the game's afoot. We're planning on opening the observatory on May 1. We're going to do the first and third Saturdays as an experiment to see if we can do it. I'd like to have a dress rehearsal down at the observatory on the 17th of April, so we can see if we've got everything figured out how to do it and project the images to a screen outside. And we also need to have a work party to do some cleanup and finish putting the dome back together. So if anybody can help next Saturday, April the 3rd, I plan to be down there doing some painting and putting the baseboard back in the dome that's still taken out since spring of 2020. I guess we're going to try to get the thing back together before we have the public down. And that's all I have to say at the moment.
All right, David. Well, that's a start. I'm looking forward to the actually having Powell back open to the public again. It's been a long time. So, all right, David, thank you.
What time next Saturday, David?
What was that, Jackie?
What time next Saturday is a question.
I'll be there at 10 o'clock.
AM?
Yeah, for a work party. I don't do those at night, little girl.
Okay. All right. So typically we'd have an update from the DSS. I don't believe Scott's able to make it this evening. Let me check real quick. Nope, I don't see him here. So last time I talked to Scott, DSS is ready. Well, it's been ready all year round. Now, obviously, the COVID has slowed things down a little bit, but I believe he said he will be installing the hot water heater the first weekend of May, so showers will be available. We do have one of the red light strands on the kitchen area. The red LED strands died. There's two, so you still have lights. That'll get replaced or fixed sometime in the next month as well. So other than that, they've been getting a lot of rain down there. So as always, he asks if you decide to go down to the DSS, before you drive out onto the observing field, please park in the graveled area in front of the REVB and then walk the field, because if it's real soft, we ask that you don't drive your vehicle out there. You can set up in the driveway and still run extension cords out to the power. It has gotten pretty soft at times that if you get stuck, then you're going to have to be towed out. And if you leave ruts, we want you to fill them back in, which is not much fun. Also, Scott told me that the neighbor's cattle got through the fence, and be wary of meadow muffins that are around in the observing field. So probably around June, there'll be some very, very, very green, tall grass in certain areas of the observing field. Other than that, though, everything's ready to go for the DSS. We're continuing our second Saturday astronomy on Saturday, April 10th. Jackie Beicher, our very own Jackie Beicher, is going to be giving a presentation on the International Dark Sky Association. And actually, Jackie, if you wouldn't mind starting your audio and video, if you could tell us, give us a little preview of what your program is going to be about.
On the April 10th, I'm going to talk a little bit about the international IDA, International Dark Sky, but I'm also going to talk about the Missouri chapter, which was started about 2 years ago. And we're doing a lot of good work around the state of Missouri, and I'll talk to you about some of that and how you all can help. And then keeping up with that theme, I've been around astronomy and amateur astronomy in this country for a long time, and many, many, many years ago at a league convention, I met a guy named Tim Hunter and his buddy David Crawford, and both of those guys started the International Dark Sky Association in, I think it was 1967, and it's grown from there. I mean, they have chapters all over the world. It's just incredible, and a lot of dark sky cities and sites around the world. So he's going to be our general meeting speaker in April. And he's also going to talk about his remote observatory, the fun and games of having one of those, which might interest some of you. Then in May, our speaker is going to be David Eicher. He's the editor of Astronomy Magazine, and he's going to talk to us about his latest book called Galaxies, which I have a copy, but I left it in the other room. So, hey, that's what he's going to talk about.
Alan Lehman just passed on a message from Melinda about the library. This is real short. Basically, if anybody wants to contact, check out or return any books from the library, please contact Alan. His email address would be treasurer@askc.org. He's also listed on the inside, the right-hand column of page 2. So that's all I've got from that.